Imagine living next to an ocean that covers most of the planet and still being told you might not have enough water to drink. That sounds impossible, but it is already becoming a serious problem in some of the driest and fastest-growing regions on Earth. The strange part is that Earth is not running out of water. We have enormous amounts of it. The problem is that most of it is salty, and turning that endless supply of seawater into affordable fresh water has been one of engineering's biggest challenges. For decades, the basic solution has been reverse osmosis. It works. In fact, it supplies drinking water to millions of people around the world. But there is a catch. You have to push seawater through extremely fine membranes under very high pressure. Those membranes can become clogged by minerals, organic material, and other contaminants. Keeping the system running requires energy, maintenance, cleaning, and eventually replacement of the membranes. And then there is the leftover salt. After fresh water is separated, the remaining water contains a much higher concentration of salt and other dissolved materials. Managing that concentrated brine can be expensive and environmentally challenging, especially for large coastal facilities. So the question has never really been, can we remove salt from seawater? We already can. The much harder question is this: can we do it cheaply, continuously, and at a scale large enough to support entire cities, farms, and industries? That is where a different approach to desalination becomes interesting. Instead of relying entirely on pressure-driven membranes, researchers and engineers have been exploring thermal methods that imitate something nature has been doing for billions of years. The water cycle. Think about what happens when sunlight hits the ocean. Water evaporates. The salt stays behind. That vapor eventually becomes clouds and returns as fresh water. Nature separates enormous quantities of fresh water from seawater without using a single plastic membrane. The challenge is copying that process without spending enormous amounts of energy. Simply boiling seawater in a giant tank is not a great solution. As more water evaporates, the remaining liquid becomes increasingly salty. Minerals can build up on heated surfaces, reducing efficiency and creating another maintenance problem. So engineers have been looking for ways to control evaporation much more precisely. One promising concept uses very thin layers of seawater, controlled heat, pressure differences, and carefully designed surfaces. Instead of heating a massive tank of water, the system can spread seawater across specialized surfaces and encourage water molecules to leave the liquid as vapor. The vapor contains vastly less salt than the original seawater. That vapor can then be collected and condensed into fresh water. Meanwhile, the salt becomes increasingly concentrated in the remaining stream. This approach changes the engineering problem. Rather than forcing salty water through a filter and constantly fighting everything that sticks to the membrane, the system is trying to separate water and salt by changing their physical states. Water becomes vapor. Salt stays behind. And that difference is incredibly important. Because if the system can control where salt crystals form, it may reduce one of the biggest headaches in desalination, fouling. There is another fascinating possibility here. The energy needed for thermal desalination does not necessarily have to come entirely from electricity. Huge industrial facilities produce enormous amounts of waste heat. Power stations generate heat. Factories generate heat. Some coastal industrial facilities have access to low-temperature thermal energy that would otherwise simply be released into the environment. If that heat can be captured and used to drive part of the desalination process, the economics can potentially improve. The same idea can apply to renewable energy. Wind and solar power do not always produce electricity at exactly the moment consumers need it. A desalination facility could potentially use available energy during periods of lower demand, turning electricity that might otherwise be curtailed into something much more valuable, fresh water. And this matters because water is becoming increasingly important to modern technology. Take semiconductor manufacturing. The chips inside phones, cars, computers, and artificial intelligence systems are produced through extremely complicated manufacturing processes. Those factories require highly purified water for cleaning and processing. Now think about the giant data centers being built to support AI. They need enormous amounts of electricity. They also need cooling. And depending on the cooling design, water can become an important part of that equation. At the same time, agriculture remains one of the largest users of fresh water. So water is no longer just a household issue. It is an industrial issue. It is an agricultural issue. And increasingly, it is an economic issue. This is why countries with growing populations, expanding industries, and limited freshwater supplies are paying so much attention to desalination. China faces a particularly interesting challenge. A large share of its population and agricultural activity is concentrated in the north, while much of the country's water resources are located farther south. For years, China has invested heavily in enormous water transfer infrastructure to move water over long distances. But moving water across a country is expensive, and rivers, reservoirs, and underground aquifers all have physical limits. The ocean, on the other hand, is sitting beside many major coastal industrial centers. If engineers can make desalination significantly cheaper and easier to operate, that changes the equation. Suddenly, the question is no longer simply how much freshwater nature provides in a particular region. It becomes a question of how efficiently humans can turn abundant seawater into usable water, and that could have consequences far beyond drinking water. Because if cheap desalination becomes practical at large scale, it could change where factories are built, where agriculture expands, and how cities plan for the future. But there is still a major question. A technology can look impressive in a controlled demonstration and still struggle when it has to operate continuously for years. Scaling up is where the real test begins. Can the system maintain efficiency? Can it handle dirty seawater? Can it control mineral buildup? Can it operate economically? And most importantly, can it compete with the desalination systems already operating around the world? Those are the questions that will determine whether this is simply another interesting engineering experiment, or the beginning of a much bigger shift in how humanity thinks about freshwater. Because the ocean has never been short of water. We have simply struggled to unlock it efficiently. And if that problem is finally becoming easier to solve, the consequences could reach much further than the coastline. Now imagine what happens if this technology actually works at a much larger scale. The biggest change would not necessarily be that everyone suddenly gets unlimited drinking water. The bigger change could happen inside the industries that quietly consume enormous amounts of water every day. Factories, power plants, agriculture, data centers, semiconductor facilities. These industries cannot simply stop using water because a region is experiencing a drought. And that is why freshwater is becoming something much more important than a basic household resource. It is becoming part of the infrastructure that determines where economic growth can happen. Look at the American Southwest. Places like Arizona, Nevada, and parts of California have attracted huge investments in technology, manufacturing, energy, and housing. But these regions also face a basic physical limitation. There is only so much freshwater available. The Colorado River has been under intense pressure, while groundwater supplies in some areas have also declined. That creates a difficult situation. A company might have billions of dollars ready to build a new factory, but the local community still has to ask one simple question. Where will the water come from? This is especially important for semiconductor manufacturing. Modern chip factories require highly purified water during production. The exact amount varies by facility and technology, but the demand can be substantial. And when you combine several large factories with growing cities, agriculture, and data centers, the pressure on local water systems can increase quickly. The same problem appears in other parts of the world. Northern China has major population centers, farms, and industrial activity, but freshwater availability is uneven. That is one reason China has invested in massive water transfer projects and other infrastructure designed to move water toward areas where demand is higher. But there is another option sitting along the country's coastline: the ocean. If seawater can be converted into freshwater more efficiently, coastal regions could gain another source of supply without depending entirely on distant rivers or underground aquifers. That does not mean desalination suddenly solves every water problem. It doesn't. Moving desalinated water inland can still be expensive. Building plants requires capital. Energy is still needed. And every technology has its own environmental and engineering challenges. But improving the efficiency of desalination could give governments another tool. And that matters because the future water problem is not going to look the same everywhere. Some places will face drought. Others will have growing populations. Some will build massive industrial zones. Others will need more water for agriculture. And some will be trying to support all of these at the same time. This is where the idea of combining desalination with existing energy infrastructure becomes particularly interesting. Imagine a coastal industrial zone where a power facility produces electricity and also generates usable waste heat. Instead of treating that heat as something that simply has to be released, part of it could potentially be redirected toward water production. Now imagine nearby wind farms producing electricity during periods when demand is lower. That energy could potentially support water treatment and desalination. The result is a kind of industrial ecosystem. Energy produces electricity. Industrial processes produce heat. Desalination turns seawater into freshwater. And the resulting water supports factories, cities, and agriculture. The more efficiently those systems can work together, the less waste there may be between them. This is one reason desalination technology matters to the larger race for industrial development. The competition between countries is often discussed in terms of artificial intelligence, advanced chips, robotics, batteries, and renewable energy. But underneath all of those technologies are basic physical resources: electricity, land, materials, and water. You can build the most advanced semiconductor factory in the world, but it still needs water. You can build a huge AI data center, but it still has to deal with heat. You can expand agriculture, but crops still need irrigation. Technology does not eliminate these physical requirements. It simply changes how efficiently we manage them. That is why a breakthrough in something as ordinary as water treatment could become strategically important. And there is another potential advantage to the thermal approach. Instead of producing only concentrated liquid brine, some systems are designed around recovering salts and minerals as solids. That could make the waste stream easier to handle in certain configurations. Salt itself is useful. Sodium chloride is used across countless industries. Other minerals dissolved in seawater can also have commercial value. But this is an area where claims need to be treated carefully. Recovering valuable minerals from seawater is technically possible, but extracting them economically at massive scale is a different challenge. The same goes for the idea that a new desalination system can immediately produce water cheaper than conventional methods. That depends on the exact design, energy source, operating conditions, maintenance requirements, financing, and scale. A promising demonstration is not the same thing as a worldwide commercial replacement. And this distinction is extremely important, because desalination has been improving for decades. Reverse osmosis is already highly developed. Modern plants can recover freshwater efficiently, and engineers continue to improve membranes, energy recovery systems, pretreatment, and brine management. So a new technology does not have to completely destroy the old technology to matter. It only needs to solve a problem that existing systems struggle with. If a new process can reduce maintenance, use lower quality heat, operate with less pressure, or make concentrated salt easier to manage, then it could find a place alongside conventional desalination rather than replacing it overnight. And that could still be a huge development. For the United States, the implications are worth watching closely. America is investing heavily in domestic semiconductor production, AI infrastructure, electric vehicles, batteries, and advanced manufacturing. A lot of that investment is going into regions where water is already under pressure. If industrial expansion continues while freshwater supplies become tighter, water could become a hidden constraint on future growth. The solution will probably not come from one machine. It will require conservation, better infrastructure, recycling, groundwater management, smarter agriculture, and potentially much more desalination. But technologies that make seawater easier to process could become one piece of that much larger puzzle. And China is not the only country working on this problem. Researchers around the world are experimenting with membranes, thermal systems, solar desalination, electrochemical methods, advanced materials, and new ways of managing brine. So the real story is bigger than one country. It is about a global race to make freshwater more reliable. For most of human history, cities had to develop around rivers, lakes, rainfall, and underground water. But what happens when technology allows cities to depend less on those natural freshwater sources? A coastal desert could potentially become a major industrial center. A city facing chronic drought could gain another source of supply. A factory could operate with recycled water and desalinated water instead of relying entirely on local rivers. That does not mean water suddenly becomes unlimited. It means the boundary between places with water and places without it could begin to change. And that may be one of the most important consequences of better desalination. For the last century, global competition was heavily shaped by access to energy. Oil determined transportation. Gas-powered industries. Electricity enabled modern technology. But in the coming decades, another resource could become increasingly important. Water. Because without water, energy infrastructure struggles. Factories struggle. Agriculture struggles. Cities struggle. And advanced technology eventually struggles too. So the most important question is not whether the Earth has enough water. It clearly does. The question is whether we can turn the enormous amount of salt water around us into useful freshwater without creating an even bigger energy, cost, or environmental problem. If engineers can continue pushing that cost downward while improving reliability, desalination could become one of the most important technologies of the next few decades. But the technology still has to prove itself. It has to move beyond promising demonstrations and survive the real world. Years of operation, changing seawater conditions, maintenance, energy costs, environmental rules, and enormous industrial demand. If it succeeds, the impact could be enormous. Not because humans have discovered a new source of water. The ocean has been there all along. What could change is our ability to access it. And that is why this story is bigger than desalination. It is about whether technology can break one of civilization's oldest limits. For thousands of years, people built their lives around water. The next generation may be able to build water systems around technology. And if that happens, some of the places we think of as too dry for massive cities, farms, and factories could look very different in the future. The ocean is already there. The real race is figuring out how to use it responsibly.